let's talk about graphing logarithmic functions when there's quite a bit going on. I mean, yeah, it would be wonderful if we knew what log y equals log base 2 of x looks like, and then we could say, okay, so this graph, I've got to shift it 12 to the right, but it's only, everything happens 4 times as fast, so 12 to the right is only 3 to the right, and then it's 4 times as tall, but down. Once we get a lot going on, maybe conceptually this gets a little bit challenging for us. So here is the process that we could go through. We could start choosing values for x and hope that 4x minus 12 became good values. And by good values, I mean powers of 2, convenient powers of 2. Or we could be a little more clever in it. And this is a process I call rubber stamping, and we'll get into this quite a bit in trigonometry. But here's the process. We could choose a value for x, and once we chose the value for x, our next step would be to multiply it by 4, then subtract 12, and then at that point we would take log base 2 of that result, multiply that by 4, and finally subtract 3. So I'm going to create a chart of values. This is kind of like, we're kind of t-charting here, but it's a lot more clever in that I don't really want to choose a value for x here. I really want to choose values for my argument. So after I've chosen x, multiplied it by 4, subtracted 12, then I would like to have powers of 2. So I call this section of this chart the bus for obvious reasons. Got a little bus look. And once I get to this portion of it right here, I have now chosen x, multiplied 4, and subtracted 12. I want powers of 2. You know, I guess you could say, excuse me, in the windows of the bus. So it would be wonderful if this was a 2, or if this was a 4, or if this was an 8, or maybe if this was a 1, because 2 to the 0th is 1, or maybe if this was a 1/2, because 2 to the negative first is 1/2. And if I got those values as arguments, now I take log of those. Well, log base 2 of 2 is 1. 1's the exponent that turns 2 into 2. What's the exponent that turns 2 into 4? 2 is. 2 into 8, 3. What turns 2 into 1? 0. What turns 2 into 1/2? Negative 1. So I call this rubber stamping because without the values, without these values in there, in fact, I'm even going to erase them. Without those values in there, this bus area, every log base 2 graph I would do would start out looking like that. And then I just have to build down and build up from it. So again, log 2, 2 is 1, log 2, 4 is 2, log base 2 of 8 is 3, log base 2 of 1 is 0, log base 2 of 1/2 is negative 1. So once I come out of log base 2, our next step is to multiply by 4. 4 times 1, 4 times 2, 4 times 3, 4 times 0, 4 times negative 1. And then my next step is to subtract 3. Minus 3, minus 3, minus 3, minus 3, and negative 4 minus 3, minus 7. All right, here's the tricky part, though. To get from row, if I call these row A, B, C here, give myself a little bit of room. To get from A to B, I multiply by 4. To get from B to C, I subtract 12. If I subtract 12 going down, in order to go back up, I need to add 12. And I get 2 plus 12, 14. 4 plus 12, 16. I get 20. I get 1 plus 12, 13. And I get 12 plus 1/2, 12 and 1/2. In order to get from A to B, I had to multiply 4, but I'm going backwards, so I divide by 4 or multiply by 1/4. So I get 1/4 of 14. I'm just going to write it as 14 over 4 plus 16 over 4 plus 20 over 4 plus, or not plus, but 13 over 4 and 13 over 4. And let's see, 12, that's 25 halves times 1/4, 25 eighths. Okay? So what I have, what I've just created here is a T-chart. Let me go ahead and put that in a different color. A T-chart of values, X values, that produce these Y values. And if I plot those, I'm in good shape. We ought to start off with 4x minus 12. It can never be 0. In fact, it can never be negative. So x cannot be 3. And now let's take a look at what our chart's going to look like. I see I need y values up to 9, perhaps down to negative 7. I need x values. What's my smallest x value here? Let's see. That would probably come from, oh, what do I have? This is almost 4. Here's 4. I've got a 5. There's close to 3. So I need x values from like 3 to 5. It looks like everything's in between there. So I think I'm going to do something along this line. So here's 1, 2, 3, 4, 5. X cannot be 3. And then it seems like there's some advantage in counting by fourths if you look up the x value. Okay, and let's plot some points here. I need to go up to 9, perhaps. 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to go down to negative 7. 1, 2, 3, 4, 5, 6, 7, negative. And 14 fourths. 4, 3 and 2 fourths. 3 and 2 fourths gets me to 1. So 3 and 2 fourths gets me to 1. You see it? 3 and 3 fourths gets me to 1. Exactly 4 gets me to 5. Exactly 4 gets me up to 5. Exactly 5 gets me up to 9. Exactly 5 gets me up to 9. And now 13 fourths. Well, that's just 3 and 1/4. Just barely past 3, and I'm down to negative 3. So I'm down to negative 3 here, and that might be enough to know what's going on. 25 eighths, that's only 1/8 past 3, and now I'm down to negative 7. So I've got my graph. Ooh, it's not a very steady hand. Something like that. It should not pass the asymptote as I've drawn it there. But there is a pretty nice mechanical way to come up with values. I suspect if we were randomly choosing values for x, we might not choose those values. We might get lucky, choose 4 and 5, which give us good values, but other than that, probably not going to choose 13 fourths for x at any given point. Okay, so pretty nice mechanical process to a much more complicated logarithmic graph. Hope that's helpful. You can expect something along those lines on the test.